Okay, today we are going to add one wrinkle, but we're going to be doing something similar to what we've been doing for the past couple days. Okay, so we're going to be simplifying radical expressions, but this time with variables. So I want to go back to what we know. So in this column right here, I'm actually squaring. Okay, so after we take a look at what happens when you square something, we're going to do the reverse when we square root, because squaring and square root are inverse functions. So here we have inside the parentheses x to the first power. X to the first power is being squared, so that's x times x is going to give you x squared, or that would be an x to the first to the second power. You keep the base and multiply the exponents. 1 times 2 is x to the second. So if x squared, x to the first squared is x squared, then the square root of x squared is going to be x to the first. Okay, here we're going to square x squared. We have the entity x squared being raised to the second power. So we keep the base, multiply the exponents. 2 times 2 is going to give me 4. So here, once again, we double the exponent. 2 times 2 is 4. Now, the square root of x to the fourth, we're going to take that exponent and divide it by 2. So the square root of x to the fourth is going to be x squared. All right, take a look at x cubed. X cubed squared is going to be keep the base, multiply the exponents. 3 times 2 is going to be x to the sixth. Okay, so therefore, if x cubed squared is x to the sixth, the square root of x to the sixth is going to be x to the third. And I think you'll see the pattern after this. If you don't already see it by now, x to the fourth squared, keep the base, multiply the exponents. 4 times 2 is x to the eighth. Okay, so the square root of x to the eighth is going to be x to the fourth. So notice every single time we're squaring something, you are multiplying the exponent by 2. And perfect squares are all variables that have even exponents. X squared, x to the fourth, x to the sixth, x to the eighth. Therefore, if you're taking a square root, we can only take the square root of a variable to an even power. Okay, so x squared, the square root, we divide the exponent by 2. 2 divided by 2 is x to the first. Square root this, divide the exponent by 2. 4 divided by 2 is 2. So x squared would be the square root of x to the fourth. The square root of x to the sixth is going to be 6 divided by 2 is 3. So x to the third is the square root of x to the sixth. Okay, and the square root of x to the eighth, 8 divided by 2 is 4. So x to the fourth is the square root of x to the eighth. Okay, so we can only take the square root of even exponents. And the square root will be the exponent divided by 2. So x to that power, or y or z or whatever. Now, since squaring a variable requires multiplying the exponent by 2, only a variable with an even exponent will have a perfect square. Variable expressions with odd exponents will not be perfect squares, but we can simplify them. But we can simplify them. Okay, so I'm going to start off. My first 3 examples are only going to have even exponents so we can see the process. I'm going to use the pen tool at this point. We have the square root of 49x squared. So I'm going to break this apart into perfect squares. 49 happens to be a perfect square. Okay, so I'm going to keep that by itself. And x squared is a perfect square since it has an even exponent. So the square root of 49 is going to give me 7. And the square root of x squared, so divide the exponent by 2. 2 divided by 2 is 1. So 7x is going to be the square root of 49x squared. Okay, now let me just keep this in here for now. We've got the square root of 50, x to the sixth power. Now, the square root of 50 is not a perfect square, but we know it has a perfect square factor in it. So we're going to break this up into the square root of 25 times the square root of 2 times the square root of x to the 6th. Okay, square root of 25 I can take. It's going to be 5. The square root of x to the 6th I can take. Okay, 6 divided by 2 is going to give me 3. So x to the 3rd will be the square root of x to the 6th. Now, the square root of 2 we can't take, so it's going to stay on the end of the expression. So that will be your simplified answer. And that was your simplified answer here. Okay, now we're going to continue. We've got all even exponents. So when we break this up, we're going to have the square root of 36. Okay, the square root of x to the 4th, the square root of y to the 10th, and the square root of z to the 8th. Okay, so the square root of 36 we can take. It's going to be 6. The square root of x to the 4th we can take because it's an even exponent. 4 divided by 2 is going to be 2. So x squared would be the square root of x to the 4th. Now, the square root of y to the 10th we can take because the exponent is even. 10 divided by 2 is going to be 5. So the square root of y to the 10th is going to be y to the 5th. The square root of z to the 8th we can take because the exponent is even. 8 divided by 2 is 4. So z to the 4th is going to be the square root of z to the 8th. Okay, so that is going to be your simplified answer. And in these cases, we had a lot of perfect squares. Okay, now in the next example, or next 3 examples, it's not going to work out clean in every case. So I'm going to start over here on the left with the square root of 27. Let's change that. Let's go blue. Now, square root of 27 we can't take, but it is divisible by a perfect square, 9. Okay, so 9 times 3 would give you 27. So the square root of 9 times the square root of 3 is the square root of 27. Now, this x to the 3rd is not a perfect square. But just like we did here, where technically 27 is 3 times 3 times 3, it's the same thing multiplied by itself 3 times. But we took 2 of them together to make a perfect square. The same thing is happening here. It is x times x times x. Well, I'm going to take 2 of them by themselves to give me a perfect square. So I'm going to break up x to the 3rd into the highest even possible, and then x to the 1st. Okay, so like a portion of 27 is a perfect square, so that I can take the square root there, it's 3. Okay, but I cannot take the square root of 3. Now I can take the square root here. Square root of x squared is going to be x. So those two values are going to become the coefficient. They're going to become rational and come out of the radical. But over here, these two guys are going to stay underneath. So 3x times square root 3x would be simplest radical form. Okay, over here, let's realize that the square root of 12 is not a perfect square, but the square root of 12 does have a perfect square factor in it. It's divisible by 4. Okay, so I'm going to break up, since 12 is the product of 4 times 3, the square root of 12 is the product of the square root of 4 times the square root of 3. Square root of x to the 7th, well, it's odd, so I can't take it, but I'm going to break it up into the largest even exponent possible, and x to the 1st. Okay, x to the 6th times x to the 1st is x to the 7th. All right, and that is the largest perfect square factor we can extract. So square root of 4 we can take, it's 2. Square root of x to the 6th we can take because that's an even exponent. 6 divided by 2 is 3, so we've got x to the 3rd. Oh my God. My handwriting's awful. Okay, now that's since we took the square root, they can come, they're going to come outside. They're going to be irrational. They're sitting outside the radical, okay? But these two, we couldn't take the square root of 3. We can't take a square root of x to the first. So those two are going to sit underneath the radical. So 2x to the third square root of 3x is going to be your simplified answer. Okay. Now, last one. I know it looks complicated. We're going to break things up in a very simple fashion. It's going to there's going to be a lot of writing here, but it's okay. Taking a look at 20. 20 is not a perfect square, but it has a perfect square factor, 4. So I'm going to write this as, since 4 times 5 equals 20, the square root of 4 times the square root of 5 is going to equal the square root of 20. Okay, now x to the 5th, I'm going to have to break that up. If it's an odd exponent, it's not a perfect square, but we'll break it up into the largest even possible times x to the 1st. So x to the 4th times x to the 1st is x to the 5th. This is a perfect square. That piece is not, so it stays underneath. Now, y to the 4, well, that's an even exponent, so that's a perfect square root, so I'll just keep it by itself. Z to the 9th is odd, so I'm going to have to break it up into the largest even possible, which is going to be 8 times z to the 1st. Okay, z to the 8th times z to the 1st is going to give you z to the 9th. So now I'll take apart, I'm going to take all my perfect square factors out. Square root of 4 is 2. Okay, square root of x to the 4th is going to be x squared. 4 divided by 2 is 2, so my exponent is going to be 2. I'm going to do the same thing here. Y to the 4th is going to become y squared. And z to the 8th, okay, z to the 8th, 8 divided by 2 is 4, so I'm going to have z to the 4th. And that will sit on the outside of the radical. These are all your perfect squares. But what's left inside is going to join under 1. So it's root 5 times root x times root z is just going to be 5xz. That is simplest radical form. And we're going to be working on this on EE2 today. EE2, so only one IXL unit. I'm going to make 90 the target again, but it is going to be very difficult to get there. So you're going to spend some time working on this. We're going to do a lot of variable stuff. So we're going to Zoom on Friday. We'll do a couple worksheets, one of which is a Kudasoft to help us practice. And then when we come back next week, we're going to be working on operations, adding, subtracting, multiplying, and dividing. Now, that'll be very easy to get through once this phase is mastered. But of course, this phase is, I think, is the most challenging to get used to. Okay, guys, have a good one.